What is up, guys? Today we're going to be solving the Leetcode medium problem number 207 course schedule. So there are a total of num courses you have to take labeled from 0 to num courses minus 1. You are given an array prerequisites where prerequisites at index I is equivalent to the array of length 2 containing the elements A of I and B of I, indicating that you must take course B of I first if you want to take course A of I. For example, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return true if you can finish all courses, otherwise return false. Okay, so now let's solve this problem. So this problem can be modeled as a DAG or directed acyclic graph. We say that this graph is directed because if we represent the individual courses as nodes, we can establish a relationship between two nodes U and V, with U being directed to V as shown in this diagram here, if course U is a prerequisite to course V. We say that this graph is acyclic because a valid set of prerequisites, when represented as a graph, will not contain a cycle. A cycle means that a course is a prerequisite to itself, which is invalid. If the graph does not contain its cycle, that means that we can finish all of the courses. For example, if we take a look at this graph B, if we were to add a connection from course 2 back to course 1, it's impossible to finish all the courses because we have a cycle in the graph, right? We can go from 1 to 2 and then travel back to itself. So therefore, in this situation, if we added this connection from 2 to 1, then we would end up with a situation where we cannot finish all the courses. And a simple way to represent this graph is by using an adjacency list. And to refresh your memory, an adjacency list is a mapping of each vertex or node to all of the vertexes that we can reach from a particular vertex. So for example, in this graph, A maps to B, C, D in the adjacency list because from A we can travel directly to B, C, or D. So the general algorithm for this problem is that for every node that we have not visited yet, we are going to execute a DFS or depth first search traversal on that node. And if we detect a cycle during the traversal, then it is impossible to finish all the courses. If we did not detect a cycle during any of the traversals, then we can finish all the courses. Now, an important detail for the DFS traversal is that we need a graph coloring or labeling mechanism for keeping track of the status of the nodes. Now, obviously, a node U can either be unvisited, which means that we haven't executed a DFS traversal on that node, or visited. We finished the DFS traversal for that node, but a node U can also be in a third state called in progress, which means that we are in the process of our DFS traversal. We are still finding all of the courses that we can take if we first take course U. In other words, we detect a cycle during our DFS traversal if we end up revisiting a node that is marked as in progress. And the reason why this third state is necessary is because if a node is visited already, we don't even visit that node. If a node is unvisited, then we execute a DFS traversal on it. But if we just had two states, visited and unvisited, then the problem that we're going to encounter is going to look like this. So if we were to execute our algorithm on this graph B, and let's say that we have this connection from 2 back to 1, we're going to execute a DFS traversal on 1 because initially we haven't visited any of the nodes. We're going to execute a DFS traversal on 1, and then we're going to visit 2, and then we're not actually going to visit back 1 because we already marked 1 as visited. So if we have a third state called in progress, then when we execute the DFS traversal on 1, we mark it as in progress. Then we visit 2, then we mark 2 as in progress, and then we still go back to 1 But because we ended up back at a node that we were visiting in our DFS traversal or in progress, now we have a cycle. So we can detect that cycle using this third state. So that is the algorithm. Now let's talk about the time and space complexity. So the solution is going to run in OE plus V space complexity, or actually more commonly it's written as OV plus E, time and space complexity, with V being the number of nodes or vertices in our graph given by the number of courses, num courses, and E is going to be the number of edges in our graph given by the length of the prerequisites array inputted. So of course it's going to run in OV plus E time, because in order to traverse, the worst case scenario is that we have to traverse the entire graph, right? If there's no cycle. And that means that we're going to have to not only visit every single vertex, we're also going to have to visit every single edge as well. So that yields us OV plus E time complexity. Now the adjacency list is going to take up OV plus E space complexity. And our entire solution is going to be based upon the space complexity of the adjacency list. So our solution is going to run in OV plus E space complexity as well, because the keys of the adjacency list are going to be the number of vertices, right? And then for each entry inside this mapping, we are mapping each vertex to the vertices that we can reach from a particular vertex. And these are just derived from the edges of a particular vertex. So in total, the number of values is simply going to be corresponded to the number of edges of our entire graph. So that gives us OV plus E space complexity. So with that detail done, let's implement the solution. Okay, so we're going to implement the solution which runs in OV plus E time and space. The first thing that we need to do is store the graph as an adjacency list. So we'll use a hash map data structure for that. So we'll say hash map integer, linked list integer, adjacency list equals to new hash map integer, linked list integer. Next, we're going to iterate through all the prerequisites and update every prerequisite list of successors in our adjacency list. So for int prerequisite in prerequisites, the successor is going to be the first element in the array. The predecessor is going to be the second element in the array. Now we need to get the successors, the current list of successors for our current predecessor. And the get or default function in Java returns the second parameter if we cannot find the specified key within the mapping. We'll say successors.add successor, and then we need to update the adjacency list accordingly. Now, we need to keep track of the status of the nodes before we execute any DFS traversal. And by default, all nodes have not been visited yet. And we'll define an enum to keep track of the 3 possible statuses for a node. And I'll define the enum just in a bit. So let's define the enum. Just like that. Okay, perfect. Now for all the nodes in the graph, if we have not already visited that node, we will execute a DFS traversal on that node. So for an I equals to 0, num courses, I++, we check if that node is not visited yet. And if not, we're going to execute a DFS traversal on that. And for good programming practices, we're going to define the DFS recursion in a separate function. Now, if during our traversal we detect a cycle, we can't finish through all of the courses, because that means that we have a prerequisite that is a prerequisite to itself. Okay, so now let's write our recursive DFS function, and it's going to take in 3 parameters, of course, which is going to be the adjacency list, the statuses of the nodes, and the current course that we're on. Now let's handle the base cases first. If our current course is already visited, we do not need to proceed further, which means that if node statuses current course equals to status.visited, we simply halt the traversal. Now, if our current course is being processed, we have a cycle, because it means that during our DFS traversal, we ended up back at the same node. And we need to mark this. We need to have a variable that keeps track of whether we detected a cycle or not. So let's define that variable, this global variable, detected cycle equals to false. Now we're going to say detected cycle equals to true. We're going to say, okay, we found a cycle, and we're going to halt the execution. Now, if these 2 base cases aren't satisfied, that means we are in progress of visiting our current course. So let's mark that status. We're going to visit all the successors to the current course by referencing our adjacency list. And of course, we're going to have to call the DFS recursive traversal function on our updated 3 parameters. Now, after visiting all of our current course's successors, mark our current course as visited. And finally, after we've finished visiting all of our current node successors, we can halt the DFS traversal for our current course. And let's see if this works. Looks like we have a typo. Node statuses. Looks like we named that variable incorrectly. We have another situation where we named that variable incorrectly on line 38. Missing a return statement on line 47. Oh yes, if we didn't detect a cycle, then we obviously return true, right? I forgot to mention that. Okay, that worked. Let's submit it. Yep, and we successfully completed this problem. Alright guys, that will be it for this video. Don't forget to like and subscribe, and I will catch you guys in the next video.